and welcome. This short presentation from Comtest Networks will help you understand the effects of microfilters and POTS splitters in various home wiring configuration when deploying VDSL2 technology. My name is Natalie Michaud. I'm part of the sales and marketing team here at Comtest Networks, and I have been in the business of telecommunications for over 15 years. My colleague, Anna Malanitsa, is our Vice President. Anna holds a degree in engineering as well as an MBA, and she has been with Comtest for more than 10 years. Anna recently co-wrote a white paper on the performance of microfilters and POTS splitters in high bandwidth applications, which will be referenced throughout our presentation today. Before we get into the technical portion of our presentation, let's talk a bit about our company. Comtest Networks is entirely focused on DSL technology. We are truly experts in the field. Comtest has been manufacturing DSL splitters for over a decade. Our products are deployed worldwide in some of the largest telcos. Our engineering team has a very strong understanding of NEBs and other DSL standards. Comtest Networks has a proven track record of reliability and performance guaranteed. Now over to Anna for an overview of VDSL technology and the use of microfilters and splitters.
Thank you, Natalie. The purpose of the technical portion of the presentation is to take a look at the customer premise end of VDSL2 deployments. We will look at a variety of different installations simplified into loop representations in order to more easily compare the characteristics that will most significantly affect VDSL2 performance. First of all, what are our options for filtering and how do they affect the service rates? What are the different wiring topologies in homes and how do these affect data rates? How does this extend to a case where the customer has only DSL services at home? In DSL, voice and data services are provided over the same line of twisted pair of copper wires. The line in at the customer premise contains voice signals in the lower frequency range, up to 4 kilohertz, as well as data signals in the higher frequency range, 25 kilohertz to 30 megahertz. Phone transient events, such as ringing, switching from on-hook to off-hook, disrupt DSL service. It is essential to isolate the low-frequency POTS signals from the DSL. At the customer premise, this isolation is usually achieved in one of two ways. Option 1 is installing a master splitter at the entry point. Option 2 is installing multiple microfilters throughout the home. Let's start with microfilters. A microfilter is a low-pass filter that isolates the low-frequency signals on the line from the high-frequency signals. They are typically second-order filters. The order of a filter determines the amount of attenuation after this 3 dB point. Microfilters have 2 ports, line and POTS. They are installed in line with telephones, fax machines, answering machines, etc. Microfilters must not be installed on the DSL port. Microfilters are a popular choice because they are easily installed by the customer and do not require an installer. Microfilters are connected in parallel with the line to the modem. Any parallel connection to the line can be defined as a bridge tap. We will discuss this a little later, in more detail a little later in the presentation. In order to better illustrate this, we have simplified the home wiring diagram into a simple loop diagram, demonstrating the wiring to and inside of the home. You can see this on the bottom right-hand corner of your screen. Segment L1 is the line from the central office to the customer premise, carrying both voice and data services. The rest of the segments, L2 through L5, represent the rest of the wiring in the home. While the original diagram depicts L2 through L4 as home phones, the segments can actually represent various possible situations. They may represent an inline filter terminated with a telephonic device, an unterminated inline filter, or unterminated telephone wiring in the home. Now let's compare this to a CPE splitter. CPE splitters have 3 connections: line, POTS, and DSL. CPE splitters provide low-pass filtering between the line and POTS, They are typically fourth order or higher filters. Depending on the splitter, it may have either a high pass or an all pass filter between the line port and the DSL. There is only one splitter required per home installed at the demarcation point. The demarcation point may be in the customer home, typically in the basement, or in the network interface box outside of the home. While installation is quite straightforward, splitters are usually installed by the service provider. As you can see from the figure, with the splitter installed at the demarcation point, the modem, and therefore the DSL signal, is completely isolated from the telephonic devices and the rest of the wiring in the home. Similar to the microfilters, we can simplify the splitter installation into a loop configuration. Please refer to the diagram in the lower right-hand corner of your screen. The line segment L1 is between the central office and the line point or a certain line port or entry point at the home. L5 is the home wiring from the entry point to the modem. Line segments L2 through L4 are isolated by the high impedance of the splitter. Earlier, in the microfilter loop representation, these segments were still present on the line as bridge taps. We can take a quick look at the two side by side for ease of comparison. Again, please note that the segments L2 through L4 are bridge tapped with the microfilter installation on the left side of your screen, whereas with the splitter installed, line segments L2 through L4 are now isolated from the line to modem, or line segment L5 on the right-hand side of your screen. So the next step of the presentation is to compare these two installations and the attainable data rates. Before we do that, I would like to take a quick moment to briefly address the definition of a bridge tap. A bridge tap is an unterminated branch in a cable, or in this discussion, any branch on a pair that is not a direct connection between the line and the subscriber. Sometimes these are referred to as T-connections. In this case, we're using the term bridge tap to refer to any T or parallel connection in the copper pair, whether it is left unterminated or terminated with microfilter and or telephone equipment. Any signal that is transmitted down a copper pair will also travel down the bridge tap. So when a signal reaches the open end of the pair or the high impedance of the filter, a portion of the signal is reflected back. These reflections result in changes in insertion loss and impedance. We will take a closer look at these issues a little later on in the discussion. Now we will start to look at measured data rates with a variety of CPE configurations. These will include both daisy chain and star wiring. In all scenarios, we will look at the case of microfilters, splitters, and dry DSL. All of the tests were performed in a 17A profile over 24-gauge wire. In order to establish a baseline to compare the test results with, the data rate measurements were first taken with a direct connection from the DSLAM to the modem without any filters present. As you can see from the diagram, the loop length from the DSLAM to the demarcation point is 2,000 feet. A 3-foot Cat5 cable was then connected to the DSL modem. The first scenario we are going to be looking at is the daisy chain configuration. There's basically one set of wires run throughout the entire home with telephone outlets branching off. When using microfilters, the DSL modem is connected along the same pair of wires as the rest of the home. The diagram here shows the modem at the very front of the chain. In fact, the modem could be connected anywhere along the chain. In this case, the remainder of the chain after the modem acts as a bridge tap. The DSL signals that travel along the chain to the modem will also continue down the rest of the chain and be reflected back to the modem. The difficulty in this situation is there is very little control over where the modem is installed in the chain. However, the ideal case would be to have the modem at the very end of the chain as shown in the following slide. In this case, the modem is at the very end of the chain. By removing the chain after the modem, we have effectively removed the bridge tap. Next, we will look at the case of a master splitter in a daisy chain. Similar to what we discussed earlier, when the splitter is installed at the entry point, it isolates the home wiring from the DSL signals. A dedicated pair of wires is then run directly from the demarcation point to the modem. Now for the results. As you can see, the case with the CPE splitter has the highest data rates, 84.5 megabits downstream and 32.9 megabits up. Skipping to the last pair of bars on the chart, the typical microfilter installation has the lowest attainable data rates, particularly in the downstream, where measured data rates were 46.7% lower. This is a direct result of the bridge tap presented by the rest of the home wiring chain. You will notice, however, that what we are calling the ideal microfilter scenario has much better rates. Relative to the baseline, there is a 6% reduction downstream and a 7% reduction upstream. Since the modem is at the end of the daisy chain, there is no longer a bridge tap present on the line. Unfortunately, this scenario is not easily achievable. Homes are wired differently, and consumers would like to install their telephone and modem equipment in the way that is most convenient for them. The next wiring configuration we are going to look at is the star configuration. In this case, all of the wire pairs in a home are connected in some centralized location. In most cases, there is a distribution bridge located somewhere close to the demarcation point at the customer premise. In this situation, installing a splitter is very straightforward. The line in connects to the splitter input, and the output of the splitter connects to the distribution bridge. A dedicated pair is then wired directly to the modem. Similarly, microfilters can be used with the star configuration. Each line segment is now connected in parallel to the line to modem connection and is therefore considered a bridge tap. In the daisy chain configuration, we were able to achieve an ideal situation by moving the modem to the end of the line. Unfortunately, that is not possible in the star configuration given the parallel connections. So now let's compare the attainable data rates in star configuration with either microfilters or a CPE splitter. With the CPE splitter, the data rates are on par with the baseline, specifically 83.7 megabits downstream and 32.8 megabits upstream. However, with the microfilters, there's a significant reduction in data rates. We see a 64% reduction in the downstream and a 16% reduction in the upstream. If we compare the two filter options, splitter and microfilter, the real difference between the two is that the splitter isolates the DSL signals and modem from the rest of the wiring in the home, whereas the microfilters, with microfilters, the home wiring is connected in parallel and acts as a bridge tap. Given this, we can start to expand our discussion to the case of dry DSL. In a DSL-only application, the customer does not need splitters or microfilters since there is no POTS present on the line. But what about the home wiring? In order to illustrate the scenario, we have one more set of measurements to take a look at. The first is the daisy chain configuration we looked at originally. Here, the customer has DSL only at home. This is sometimes referred to as dry DSL or naked DSL. There are no phones or fax machines connected in the home, no splitters or microfilters. However, the existing home wiring is still present. Just as we saw in the earlier daisy chain situation with microfilters, it is impossible to determine where the modem will be installed in the chain. In the case we are discussing here, the modem is at the start of the chain, so the rest of the home wiring acts as a bridge tap. If the modem were installed at the very end of the chain, the bridge tap effect would be removed. Similarly, here we have the star configuration. Again, there are no telephonic devices or filters, but the home wiring is left in its original state. And here we have the results. In the daisy chain configuration, there is a 47% reduction in downstream and a 1% reduction upstream. In the star configuration, there is a 62% reduction downstream and a 23% reduction upstream. These reductions in attainable data rate are caused by the bridge taps that are present in the home wiring. If we want to improve the level of service at the customer premise, these bridge taps need to be removed. There are two solutions to this problem. The first is to roll a truck to the customer site and run a dedicated pair of wires from the demarcation point to the modem. If the rest of the house wiring is removed from the loop, data rates will increase back up to the baseline. The only shortcoming with the solution is that it becomes difficult for the customer or a future resident in the home to turn phone service back up. Should the customer want to go back to phone service, another truck roll will be required to reconnect the original wiring. The second option is installing a splitter at the demarcation point. This seems a little strange at first because there is no phone service present and therefore filtering is not required. However, the high impedance nature of the filter isolates the home wiring from the modem. As you can see in the graph on your screens, installing a splitter in either the daisy chain or star configuration, we see the data rates jump back up to the baseline maximum rates. An installer will need to go out to do the splitter installation and wire to the modem, but should the customer reorder telephone service, no further truck roll will be required. While the intention of these tests was to compare microfilters and splitters, the real conclusion we were able to come up with is that the home wiring has a very significant impact on DSL services. In order to understand the reduction in data rates, we can take a look at some key loop parameters. The results we will be reviewing are specific to the star configuration with 20-foot bridge taps. However, the loop parameters are important in any DSL deployment. In specific, we can measure impedance variations on the customer premise side of up to 10 times. The impedance seen by the modem is very important. For example, if the modem is designed for a 100 ohm system, the impedance of the cable should remain 100 ohms to avoid error-producing reflections and losses. At high line rates, such as those in VDSL2, these signals can be distorted if the impedance seen by the modem varies. The blue trace is the impedance when the modem is connected to a POTS splitter at the entry point. You can see that it observes a fairly steady 100 ohm impedance. Alternately, the red trace shows the resulting impedance fluctuations over the VDSL2 frequency band with 4 20-foot bridge taps present at the customer premise. Due to the above observed impedance mismatch, there is a substantial amount of insertion loss between the line and the modem. So insertion loss is the second key parameter. In this case, we see loss of up to 30 decibels. Insertion loss is the difference between the received signal for 0 length of phone line and the actual received signal in an application. Any length of cable will add some loss to the circuit. If you look at the graph on your screen, the blue trace represents the insertion loss of a 2,000-foot loop. The red trace represents the insertion loss with 4 bridge taps present on the line. Bridge taps cause reflection and add additional insertion loss to the loop. In this case, the additional insertion loss is more than 30 dB, or more than 1,000 times. Comparing to the straight line loss of cable only, the notches vary with length of bridge tap. Shorter bridge taps will cause deeper notches and higher loss of signal. And lastly, we have group delay. Group delay is the delay in the signal arrival at the receiver caused by the phone line. Again, the blue trace is the group delay with a 2,000-foot cable. You will see that the group delay in this case is a straight line. This is constant and will not bring any degradation to the system. In the case with the bridge taps, the red trace on the graph, the reflections create sharp changes in group delay. This means depending on where the data is over the frequency band, it will arrive at the receiver with varying delay, which will cause degradation of the received signal. In summary, the bridge tap segments cause changes in impedance, insertion loss, and group delay. The variation in these parameters is caused by the signal reflection, which in turn results in less power being transferred to the modem and very significant changes in attainable data rates. Homes are all wired differently. In order to provide the best level of service possible, it is necessary to remove the home wiring from the equation as much as possible. CPE splitters eliminate bridge taps in home wiring by isolating the DSL at the demarcation point in the home. This concludes the theoretical portion of our presentation. I will now hand over to Natalie for a quick overview of Comtest Splitter product line.
Thank you, Anna. So from what we've seen today, there are a few good options available for filtering voice and data. But depending on the home wiring, some options are clearly better than others. Anna demonstrated that some very common home wiring configurations could have a serious negative effect on performance if voice and data filtering is not managed properly with the right device. I trust you have noticed the results of installing a master splitter was clearly better than microfilters. Even in the case of a single VSL line without telephone service, installing a master splitter at the entry point can eliminate potential problems and unnecessary truck rolls. So as I mentioned at the beginning of the presentation, Comtest Networks business is all about POTS splitters. We have all types for all applications. Comtest Networks manufactures a full line of test access and splitter systems for central office and remote cabinets. We have partnerships with many VSLAM manufacturers such as Zone, Calyx, and Ericsson. We develop CPE, NID, and multi-dwelling solutions for all versions of VSL up to VDSL2 in both ANSI and ETSI standards. Our splitters are backwards compatible to legacy ADSL technology. We comply with Telcordia, CSA, UL, and NEBS requirements, and we pay close attention to the performance aspects such as noise reduction, ring tripping, and on-off hook transitions. I wanted to show you, just put in a few words actually, on our latest NID splitter, which clips in perfectly into most standard NID telco boxes. It has gel-filled IDCs and a make-before-break connector to verify dial tone without having to disconnect anything. It is our most popular CPE splitter, and I would be happy to send you a sample if you would like to contact me. Beyond our own portfolio of products, we offer custom design services as well. Our product development, manufacturing, testing, and quality control are all done on site, making Comtest Networks the ideal partner to work with. So this concludes our presentation. We hope you enjoyed it. If you have any questions or comments or would like to discuss a specific application with a member of our technical team, please feel free to contact me and I can set it up for you. And as I mentioned before, I could send samples of any of our products depending on your requirements. Thanks again, and goodbye.